Still getting affected by the storms last night, really bad.
And they never got this, well, they didn't get as far as Yukon. I don't live in El Reno. So I don't know about El Reno, but I don't know that they got this far. They kind of stayed west, which was all right by me.
I had to stay in Texas last night and I was watching it spin right over our house.
They were saying that they were, they had a tornado near Eric. I don't know that it actually hit anything, but
It was out in, it only lasted like 2 miles. It was out in the middle of a wheat field.
which is good. All right. Well, I had prepared to talk about the exam and then I forgot to look at the average. But after I graded them the other day, the average was just fine. So it was well into the 80s probably. So I got nothing to complain about there. You did pretty good. And we're going to start a new module today. We're going to start our module 3. And it's going to cover, now I forget how many chapters it covers. How many chapters does it cover? And then we'll get this done, get the test done. And then the last module only covers 2 chapters, I believe. So it's a little bit more condensed. All right, so we're going to talk about confidence intervals today. And as I was pondering confidence intervals this morning, it occurred to me that we probably should review what statistics is all about. And from the beginning of the semester till now, we've talked about populations and samples and how statistics is a method, a mathematical method, to give us some insight about a population. So, for example, I hear there's an election coming up in November. Have you heard that? And we are every day somebody puts out a poll comparing what percentage each of the 2 candidates, if the election was held today, would get. So that is statistics used to predict something about a population. So they take a survey, they get a proportion. So they actually find what percentage of people say they would vote for either candidate. And then they report those statistics, but they report those statistics with a margin of error. So they report them as representing what's going to happen in the population in the election in November. And they report it with a margin of error. So the margin of error gives them some wiggle room with their predictions. And so what they say is, let's say Biden has 40% of the vote, plus or minus a 0.5 percentage point. So he could have, what they're saying is the proportion somewhere in between 39.5 and 40.5. So if using the methods that they use to gather these statistics, the proportion of people voting for him are somewhere in between those 2 values. And that's what a confidence interval is. And we have 2 kinds of confidence intervals, one for the mean and one for the proportion, which is what a election poll survey is. It's a proportion. So it's going to be an interval of values that we have some confidence that the true population mean is somewhere in between those 2 values. Or it's an interval of values that we have a certain probability or a certain certainty that the true population proportion is somewhere in between those 2 values. So it's just another method of using data from a sample to predict what's happening in a population. So we're going to calculate and interpret confidence intervals for estimating a population mean and a population proportion. And again, a proportion is just a relative frequency. So it's how many out of how many say they're going to vote for one of the two candidates. We're going to talk about the student's T probability distribution, and not to be a nerd, but I am. I freely admit it. On my trip to Colorado, we were discussing the Guinness Brewery because my brother-in-law and sister have visited the Guinness Brewery in Ireland. And we were talking about how the student's T probability distribution originated at the Guinness Brewery in Ireland. That's where it started. We're going to discriminate between problems applying the normal and the student's T. Where would you apply the standard normal distribution to a problem versus the student's T? And then the last but not least, how do statisticians know how many of the population they have to survey to get a large enough sample to do what they want to do? And there's actually a formula for that. And when we get to that formula at the end of this chapter, it's one of those formulas you want to write down on your piece of paper you're going to bring in for the next exam. As a matter of fact, you want to write it down so you can do the homework, because invariably every semester I get question after question after question. How do I calculate the sample size? I said, I gave you a formula for that. There's a formula for that. All right. Have you ever wondered, probably not, have you ever wondered what the average number of M&Ms in a bag at a grocery store is? Because every bag is not going to have exactly the same number. They should be pretty close. But, you know, error does happen when you're manufacturing something. You can use confidence intervals to answer this question. Okay, so we're going to first look at confidence intervals of a single population mean using the normal distribution. So the first one we're going to look at is finding that range of values where the population, we're fairly confident the population mean is somewhere in between, and we're using the normal distribution. Do I want to show you this video? I think I'll skip it. So if you want to go watch the video, it's in the slides. We use sample data to make generalizations about an unknown population. That's what we do. That's what we've been doing. The sample data help us to make an estimate of a population parameter. We realize that the point estimates is most likely not the exact value. If you take a sample and you calculate the mean, chances are that's not the mean of the population. But it's close. After calculating the point estimate, so either a mean or a proportion, we construct interval estimates called confidence intervals. This part of statistics is called inferential statistics because we're inferring something about the population based on the sample that we took. Okay, so here are our 2 point estimates and what we're talking about with interval estimates. If you're trying to determine the percentage of times you make a basket when shooting a basketball, you might count the number of shots you make and divide that by the number of shots you attempted. That's a sample. And what you've calculated is a proportion. That percentage of shots were made. In this case, you would have obtained a point estimate for the true proportion. And we use P with a hat over the top of it to say that is the sample proportion. So P hat is a point estimate of the true proportion. So whatever the true proportion is of all the shots you ever made in basketball, that sample you did, that is a point estimate of the true population of all the shots you ever made. And we use P hat to represent that. Suppose you were trying to determine the mean rent of a 2-bedroom apartment in your town. You might look at the classified section of the newspaper they still do have classified sections of newspapers. Does anybody take a newspaper? We still take a newspaper. We take the Yukon Progress. You might look at the classified section of the newspaper, right? Or maybe you go to Zillow and look at properties for rent. That would work too. You write down several rents listed and then average them together. You would have obtained a point estimate of the true mean. So you took a sample of all the rentals in your area. You calculated the mean of that sample. The mean of that sample is a point estimate of the true population of all the properties for rent in your area. And we use X with a bar over the top of it. So we use P for the population proportion. We use P hat as the sample proportion, which is an estimate of the population proportion. So P, there you go. P is the population proportion. P hat is the sample proportion. It is an estimate of the true population proportion. Mu is what we use for the population mean, the Greek letter mu. And X bar, the average of the sample, is a point estimate of the true population mean. All right, what's a confidence interval? A confidence interval is another type of estimate, but instead of being just one number, it's an interval of numbers. It provides a range of reasonable values in which we expect the population parameter to fall. There's no guarantee that a given confidence interval does capture the parameter, but there is a predictable probability of success. Okay, I'm thinking the world's against me this morning. My cup broke. First PowerPoint goes away and now my cup breaks. All right. So in chapter 7, we discussed the central limit theorem, and you may have already forgot the central limit theorem, but the central limit theorem says that if I have a population, whether the distribution of that population is normal or not, if it's normal, then we can use the central limit theorem based on any size of sample we want. If the underlying distribution is not normal, let's say it's uniform, then we need to pick samples from that population of size 30 or greater. Central limit theorem says that the distribution of sample averaging, so you take multiple samples from a population and you calculate the average of each of those samples, the distribution of the sample averages will be normal. And the standard deviation of the distribution of sample averages, called the standard error of the mean, is sigma over the square root of n, where n is the size of your sample. So suppose we do not know the population mean mu of the number of songs a consumer downloads a month from iTunes. But we do know that the population standard deviation is 1. So in this case, we actually know from historical data the population standard deviation. If we take a sample size of 100 and calculate the sample mean of 2, then by the central limit theorem, the standard deviation for the distribution of sample means is sigma over the square root of n, which would be 1 over the square root of 100, which would be a tenth. Okay, remember the empirical rule, the 68, 95, 90, what is it, 99 and a half, I can't remember. The empirical rule, which applies to bell-shaped distributions, says that in approximately 95% of the samples, the sample mean will be within 2 standard deviation of the true population mean mu. So for our iTunes example, 2 standard deviations from the mean would be 2 times 0.1 or 0.2. Because X bar, the mean of the sample, is within 0.2 units of mu, the population mean, so the sample mean will be somewhere between the population mean plus or minus 2 standard deviations in 95% of the samples. Because X bar is within 0.2 units of mu, which is unknown, then mu is likely to be within 0.2 units of X bar in 95% of the samples. The population mean mu is contained in an interval whose lower number is calculated by taking the sample mean and subtracting 2 standard deviations, and whose upper number is calculated by the sample mean and adding 2 standard deviations. In other words, mu is between X bar minus 0.2 and X bar plus 0.2 in 95% of the samples. That is by the empirical rule. Okay, so X bar, let's say X bar is 2. So the mean of the sample is 2. So if I take 0.2 from 2, I get 1.8. And if I add 0.2 to 2, I get 2.2. So we say that we are 95% confident that the true population mean, which we don't know, is somewhere between 1.8 and 2.2 songs per month. So the 95% confidence interval is from 1.8 to 2.2. And this is interval notation, which you may or may not remember from algebra. And I always say that the way we write things in mathematics, sometimes we use the same notation for more than one thing. So you do need to know the context in which this is used. So if I have 2 numbers separated by a comma with parentheses around them, that could mean one of 2 things. It could be the ordered pair in the coordinate plane that you plot, 1.8 in the x direction, 2.2 in the y. But that's not the context we're using that notation. We're using that notation in the context of an interval. So what that means is, if I draw a number line and I put 1.8 on it, and I put 2.2 on it, that mu is somewhere in between those 2 numbers 95% of the time, or mu is less than 2.2 and greater than 1.8 in 95% of the samples, 95% of the time. So that's what that means, that the true population mu is somewhere in between 1.8 and 2.2, somewhere in there, 95% of the time. The 95% confidence interval implies 2 possibilities. Either the interval 1.8 to 2.2 contains the true mean mu, or our samples produce an X bar that is not within 0.2 standard deviations from the true mean mu, or 0.2 units, not 0.2 standard deviations. The second possibility happens only 5% of the time. So 95% of the time, the true population mean is somewhere in between 1.8 and 2.2. 5% of the time it isn't. And that's what confidence levels tell us. It tells us the confidence level we have that the true population mean is somewhere in between those two values. 100% minus my confidence level is the number of times that true population mean isn't between those two values. Remember that a confidence interval is created for an unknown population parameter like the population mean mu. Confidence intervals for some parameters have the form the point estimate, which in our case was the mean of the sample. It could also be a sample proportion minus the margin of error to, so you start there, to the point estimate plus the margin of error. The margin of error depends on the confidence level that you choose. We use 95% because we happen to know from the empirical rule that 95% of our data is going to be plus or minus 2 standard deviations from the mean. That's something we learned about the normal distribution. But you can pick any confidence level you want. The margin of error depends on the confidence level or percentage of confidence and the standard error of the mean. So to find the confidence interval, we need to pick a confidence level, and then we're going to use that confidence level to find a z-value, and then we're going to multiply that by the standard error of the mean to get that plus or minus value that we add or subtract from our point estimate. Is that complicated enough? Yeah. When you read newspapers or journals, some reports will use the phrase margin of error. That is that standard error of the mean times your z-value. Other reports will not use that phrase, but include a confidence interval as the point estimate plus or minus the margin of error. These two ways of expressing the same concept. Okay, how do you construct a confidence interval for a single unknown population mean, where the population standard deviation is known? Okay, if you know the population standard deviation, you're going to use the normal distribution. If you know the population standard deviation, you're going to use the normal distribution. Now, whether or not that's realistic, I don't know. But we're going to assume you know it. So any problem that you have in homework where they say the population standard deviation is, you're going to use the normal distribution. Okay, here the margin of error is called the error bound for a population mean. We abbreviate that EBM. The confidence interval estimate will have the form the point estimate, whether that's a mean or a proportion, minus the error bound, to, so you start at that endpoint on the left, point estimate minus the error bound, to the point estimate plus the error bound. So what you have to calculate is the error bound. You know the mean of your sample, you took the sample, so you know that. You know the population standard deviation, you know sigma, you know the size of your sample, that's n, and then you've got to figure out what confidence level you want to use. That's going to help you find a z-value, and then you're going to calculate that error bound to the mean. The margin of error, the EBM, depends on the confidence level, abbreviated CL, and that is something you choose as a statistician. The confidence level is often considered the probability that the calculated confidence interval estimate will contain the true population parameter. However, it's more accurate to state that the confidence level is the percent of confidence intervals that contain the true population parameter when repeated samples are taken. There is another probability called alpha. Alpha is related to the confidence level. As a matter of fact, alpha is 1 minus the confidence level, or alpha plus the confidence level is equal to 1. So in the previous example, we used a 95% confidence level because we knew from the empirical rule that that would give us plus or minus 2 standard deviations from the mean. So alpha is 5%. So if we're 95% confident that the true population parameter is somewhere between those two numbers, we're 5% confident that it isn't. So alpha is our level of not confidence, if you want to say it that way. And we need alpha. Alpha is how we figure out our Z value. So if we're 95% confident, 5% would be alpha, and we're going to use that to find Z. Okay, for example, suppose we've collected data from a sample. We know the sample mean, but we do not know the mean for the entire population. The sample mean is 7, and the error bound for the mean is 2.5. So in this case, they gave me the error bound. I'm not calculating it right now. So what's my confidence interval? Well, if my error bound for the mean is 2.5 and my sample mean is 7, what's my lower limit of my confidence level interval? Is it 7 minus 2.5? So our lower limit of our confidence interval is our sample mean minus the error bound. And what's our upper limit? So our confidence interval is what? 4.5 to 9.5. So we put those two numbers separated by a comma inside parentheses. So we're 90, whatever confidence, I don't know what the confidence level is. So we're somewhat confident. Since there's no confidence level stated here, they just gave me the error bound. I could figure it out. I am confident that the true population mean is somewhere between 4.5 and 9.5. Myself caught up here. All right, if we said the confidence level is 95, so let's assume that this error bound was calculated using a confidence level of 95%. We would say that we are 95% confident that the true population mean is somewhere between 4.5 and 9.5. Okay, how do you find the Z-score so that you can use this to find the error bound of the mean? A confidence level for a population mean with a known standard deviation is based on the fact that the sample mean follow an approximately normal distribution. That is the central limit theorem. It says that if we have a distribution, whether the underlying distribution is normal or not, if we take samples from that distribution and calculate the means, and then look at the distribution of the means, the distribution of the means will be normal. That's the central limit theorem. We know that the population we know this population standard deviation, we know sigma. We use a standard normal distribution to calculate the error bound of the mean, and then we construct the confidence interval. So we need to find the value of Z using the standard normal distribution that puts an area equal to the confidence level in decimal form in the middle of the standard normal curve. Okay. The Z-score that has an area to the right of alpha over 2 is denoted by Z subscript alpha over 2. For example, let's say your confidence level's 95%. That's a very common confidence level to use. Then alpha is 1 minus 0.95. Alpha's 0.05. Alpha over 2 is 0.05 divided by 2, which would be what, 0.025? So we need to find the area to the right of Z 0.052. Excuse me. Let me draw this. So here's the standard normal curve with a mean of 0 and a standard deviation of 1. 95% of the area is somewhere between these two Z's. So this is 95%, 0.95. So in each tail, is going to be 1 minus 0.95 over 2. So in each tail is going to be 0.025. So this is 0.025 in this tail, and this is 0.025 in this tail. So to find Z sub alpha over 2, so mad they changed PowerPoint. Okay, so to find Z sub alpha over 2, we need to find the Z value for an area to the left of that equal to what? Well, the area to the left is this tail over here, the 0.025, plus the 0.95. So the area from Z sub alpha over 2 to right there is 0.95. The area in this tail to the left of negative Z sub alpha over 2 is 0.025. So the area to the left of that Z right there is 0.95 plus whatever's in that tail over there on the left. So what's that, 0.975? So the area to the left of that Z right there is 0.975. Can I find Z sub alpha over 2 then? Yes, because you can use an inverse normal. So Z sub alpha over 2 is inverse normal, and I'm out of room. What's the area? 0.975? 0, 1? So what is that Z sub alpha over 2 there? Does anybody got a calculator? Pull out your calculator and calculate that. Give it to me. State it to 2 decimal places. What'd you get? What'd you get, Charlie? Where's your inverse normal? Second distributions, right? Is it number 3? What'd you get?
1.9.
Okay, now everybody listen to me. Are y'all listening? For every 95% confidence interval, Z sub alpha over 2 is 1.96. All of them. Because that Z sub alpha over 2 is based on the fact that 95% of your areas between Z sub alpha over 2 and negative Z sub alpha over 2. So that is the Z level for every single confidence level that's 95%. So if you find one at 98%, can you write that down? At 98% Z is whatever? Sure. As a matter of fact, that's what we used to do. Well, that's not helpful. Can I say again how displeased I am that they took my PowerPoint away from me? My gosh. Okay, so this is how you calculate the error bound of the mean. The error bound of the mean is that z sub alpha over 2 that corresponds to your confidence level times the error bound of the mean. So it is z sub alpha over 2 times sigma over the square root of n. Then you're going to subtract that error bound of the mean from your sample mean to get the lower limit of your confidence level, and you're going to add it to your sample mean to get the upper limit of your confidence interval. He is displeased with Microsoft. Of course, it could be that my mouse died. No, it's Microsoft. All right, let's try this again. All right. Suppose scores on exams and statistics are normally distributed with an unknown population mean and a population standard deviation of 3 points. Now, as soon as I see that they give me the population standard deviation, I know I'm going to use the normal distribution. A random sample of 36 scores is taken and gives a sample mean of 68. Find a confidence interval estimate for the population mean exam score. Find a 90% confidence interval for the true population mean of statistics exam scores. Okay, so what do I need to do? I need to find the error bound of the mean. And the error bound of the mean is z sub alpha over 2 times sigma over the square root of n. And the z sub alpha over 2 depends on my confidence level. So I'm going to draw a picture. My confidence level is 90%. So between this negative z sub alpha over 2, which I never find, by the way, I could, but I don't. It's just the opposite in sign of z sub alpha over 2. And z sub alpha over 2 is over here. And 90% of my data is between those two values. Okay, so now I'm going to find the area in the tails. So I'm going to take 1 minus my confidence level. That'll give me alpha. 1 minus the confidence level. 1 minus 0.9. Is that 0.1? And then I'm going to divide that by 2. That is going to be 0.1 divided by 2. Is that 0.05? So right there is 0.05. So the area to the left of Z is what? 0.95. So area to left, which is what I need to be able to put this in my calculator. Area to left of Z sub alpha over 2 is 0.95. So I do an inverse normal. Z sub alpha over 2 is inverse normal 0.95, 0, 1. What you get? And this one you'll probably estimate to 3 decimal places because it's 1.645. Is that what you get? So for every 90% confidence level, is Z sub alpha over 2 1.645? Do I have any more room here? Yes, I do. Okay, so Z sub alpha over 2 is 1.645. So my error bound of my mean is Z sub alpha over 2 times sigma over the square root of n. So that's 1.645 times what was sigma? 3. And what was n? 36. So you take 1.645 times 3 over the square root of 36, and I get approximately 0.8225. So my error bound, my margin of error is 0.82. Okay, so then how do we find the confidence interval? Takes X bar and subtract the error bound of the mean. Take X bar and add the error bound of the mean. And that is your confidence interval. So what is that? X bar minus the error bound of the mean. What was our mean? 68. And then we take X bar plus the error bound of the mean. 68 plus. So what's our interval? Our interval is 67.1775 to 68. Oops. 0.825225. So we are 95% confident that the true population mean is of statistics scores is between 67.2 and 68.8. All right, would you like to find the easy way to do this? Would you like to know the easy way to do this? Do you suppose your calculator can do this? Of course it can. Can your calculator find confidence intervals? Oh, sure. I always hesitate to show you. I figured at least the majority of you, the vast majority, would figure out how to do this on your calculator anyway. So I might as well show you. So let me go to the calculator. All right, so on your calculator, we're going to go to, make sure I go to the right place, to our distributions, I think. Is that where we're going? Nope, I already forgot where I'm going. There we go. Oh, get it. Okay, I got it. I've been a week, been off a week. Okay, so you're going to go to your stat menu and you're going to arrow to the right till you get to tests. And if you look, there's all sorts of spiffy tests in here, which we will be using later. But number 7 is Z interval. So that is when you know the population standard deviation and you're using the normal distribution, you normally would be finding a Z score. So we're going to use the Z interval to find that confidence interval of the true population mean. So we're going to use number 7. Number 8 is if you don't know the population standard deviation, which we will talk about later. So we're going to use number 7 for now. And you'll see that number 7, you can either use the statistics you know, so you've already calculated the mean of the sample and you know the population standard deviation, or you can use data. So you can plug in data, which we are going to do. I have it right here. We can plug in data and let the calculator calculate the mean and standard deviation for me. Okay, but I'm going to use stats. And I'm going to plug in the population standard deviation, which I was given, correct? I know the population standard deviation. Was that 3? Yep, so we're going to type that in. And then the mean of my sample, what was my mean? What was my mean? 68? And my sample size was what, 36? And what confidence level did I use? 0.9? So with a standard deviation of 3, a mean of 68, sample size of 36, and a confidence level of 90%, do we get an interval from 67.178 to 68.822? Is that exactly the same answer we got before? Okay, so I messed it up at the beginning because I've slept since a week and a half ago. So where do you find the confidence intervals? Stat, arrow over to tests, and then the Z interval is what we're using right now. Okay, are you ready? I got data. I printed it out a lot. So I want you to put this data in your calculator in a list, whatever list you want to use, L1, L2. You don't have a calculator, do you? I'm gonna grab one. So at least y'all can look at it together. I'll grab a calculator real quick. Those of you who have your data, go ahead and start putting it in your calculator.
Put your button in there, be a lot easier.
My granddaughter was playing with it last night, so there's no telling what it was. The stat, edit. And Excel will do this also, by the way. It will find confidence intervals for you. So if you're thinking about, getting a job and your boss asks you to find a confidence interval, you'd probably use Excel or some statistical software. There's lots of stat software out there. But for our purposes, the calculator works very well. And believe it or not, I did put this data in my calculator before spring break, and it disappeared. I'm not sure why software is doing what it wants to these days. And I hope I don't make a mistake putting this in. And I'm gonna go calculate the one variable statistics, just so that we can see if we all have the same data. Okay, that was a comma. Let's go back there. We all get the same one variable statistics, and the chances are we've all put the same data in. And there should be 30 data values. Have you got 30? All right. So I put mine in L3 because I don't know what L1 and L2 is. That's probably functions and modeling, but I go ahead and put that. All right. Mumble. So I'm going to go back in and I'm going to go stat calc, the one variable stats for L3. That's where I put my data. I don't have our frequency list, calculate. So is that what you got? 1.0237333? Is that what you got for your mean? Did you get something different? Did anybody get that for their mean? Or am I off? Is that what you got? Okay, is that what you got for your standard deviation S sub x 0.4029167736? Okay, that means I put my data in correctly. All right, let's go back to PowerPoint. The specific absorption rate for a cell phone measures the amount of radio frequency energy absorbed by the user's body when using the handset. Every cell phone emits RF energy. Different phone models have different SAR measures. To receive certification from the Federal Communications Commission for sale in the United States, the SAR level for a phone must be no more than 1.6 watts per kilogram. The table, which I gave you a copy of, shows the highest SAR levels for a random selection of cell phone models as measured by the FCC. Find a 98% confidence interval for the true population mean of the specific absorption rates for cell phones. Assume that you know the population standard deviation is sigma equals 0.337. Okay, so I'm going to go back to my calculator because I put the data in. And I am going to use my stat test Z interval number 7. But now, instead of using stats that I calculated, I'm going to use the data I inputted. So I'm going to highlight data and hit enter. Okay, so now I need to input what the standard deviation is that they gave me. So the standard deviation of the population was what? 0.337. So we're going to put that in, 0.337. And I put my data in L3. So I'm going to tell my calculator that. And what confidence level do I want? 0.98. So we can be 98% confident that the true population mean of SAR rates is somewhere between 0.88 and 1.67, 1.167, with a mean of 1.0237 and a standard deviation of the sample to be 4.4029. Now, the slide deck does have the calculation for you. Since you're doing a 98% confidence interval, you would find Z sub alpha over 2 for what? 0.99? 0.02 divided by 2 would be 0.01. Add that to 0.98. So you'd find Z sub alpha over 2 by finding the inverse normal for 0.9901. That happens to be 2.326. Multiply that by the standard deviation divided by the square root of 30, and you get 1.431. So the error bound of the mean is 1.431. Add that to your mean of your sample, which you found using the data. Subtract that from the mean that you found from the data, and you get the confidence interval. Your calculator just does it for you. Okay, what effect does changing the sample size have? Okay, if you increase the sample size, then n gets bigger, and n is in the denominator of a fraction. If you increase the denominator of a fraction, you decrease the fraction. It gets smaller. As the denominator gets bigger, the fraction gets smaller. So the error bound of the mean will get smaller as your sample size increases. So if that's one way to decrease the error bound, is increase the sample size. Decreasing the sample size, if you have a number in the denominator of a fraction and you make it smaller, the fraction gets bigger. So the error bound gets bigger if you decrease the sample size. So one way to decrease the error bound of the mean is to increase the sample size. Okay, what effect does changing the confidence level have? Well, the confidence level size is what Z is based on. So if you increase the confidence level, the error bound becomes bigger and it makes the confidence interval wider. So the smaller or the larger your confidence level, the wider your interval gets. If you decrease your confidence level, then you decrease the interval, your confidence interval, because it affects the Z size. The more confidence you choose, you notice that the 0.98 confidence level, the Z score was a lot larger. It was 2.2 something compared to a 95% confidence level where Z was what? 1.96? You can work backwards to find the error bound of the mean if you want. Suppose we know the confidence interval is 67.18 to 68.82, and we want to find the error bound. If I know the sample mean is 68, what's the error bound? 0.82. So I could do that if I needed to. And if I know the error bound, and I know the sample size, and I know the standard deviation, I can figure out the Z score, and I can figure out the confidence level. Now, you can also calculate the sample mean from the confidence interval, because the sample mean is smack dab in the middle of the confidence interval. So if you take the lower limit and add the upper limit and divide by 2, so find the average of the confidence interval, that's the mean of your sample. Okay, calculating sample size. If researchers desire a specific margin of error, then they can use the error bound formula to calculate the required sample size. So the formula for the error bound of the mean the formula is what? The error bound of the mean is z sub alpha over 2 times sigma over the square root of n. And if I want to figure out what n is, I got to do some algebra. Okay, so the first thing that I am going to do is I'm going to multiply both sides by the square root of n. Over on the right-hand side, the square root of n will cancel. So I end up with the square root of n times the error bound of the mean is equal to z sub alpha over 2 times sigma. Now I'm solving for n, so I'm going to get rid of the error bound of the mean, and I'm going to do that by dividing both sides by the error bound of the mean. So I get the square root of n is equal to z sub alpha over 2 sigma over the error bound of the mean. And then if I'm solving for n, and n is in a square root, can I square both sides? Sure. So n is z sub alpha over 2, which depends on your confidence level, sigma over the error bound of the mean squared. Now, you can square each item inside the parentheses. So the formula could also be written as z sub alpha over 2 squared sigma squared over the error bound of the mean squared. Either one works. You either do the division and then square it, or you square each one of them and then do the division. Whatever works. Whatever floats your boat. I just think the top formula is easier to use. Okay, so do people use this in actuality? Yes, they do. All the time. Especially in these presidential polls. If I have to know how many people to survey to get a certain confidence level and a certain margin of error, I use this formula and then I know how many people I have to survey. The population standard deviation for the age of Foothill College students is 15 years. If we want to be 95% confident that the sample mean age is within 2 years of the true population mean age of Foothill College students, how many randomly selected Foothill College students must be surveyed? So my formula is, so this is the information I need. I need to know z sub alpha over 2. I need to know sigma, and I need to know the error bound of the mean. Now, 2 of these values are given to you in the statement of the problem. The sigma is what? 15 years? And they give you the within. So what they're saying is that the true mean is within what, 2 years? So they're saying telling you the error bound of the mean is 2. So that's what they're giving you. Error bound of the mean. Okay, what don't they give you? They don't give you z sub alpha over 2. But do you know z sub alpha over 2 for a 95% confidence interval? Is it 1.96? Is that what I calculated earlier? Now, I could certainly calculate if I forgot that. So that means that the area that I'm shading is 0.95, which means in each tail would be 1 minus 0.95 divided by 2, correct? So right here would be 0.025. Over here would be 0.025. Do those 3 areas add up to 1? 0.025 plus 0.95 plus 0.025, 1? So what is z sub alpha over 2? Z sub alpha over 2 is what? The inverse normal of 0.975, correct? 0.1. Because the area to the left of that would be 0.95 plus 0.025. And is that 1.96? Okay, so now I know everything. Let's plug and chug. So 1.96 times 15 over 2 squared. What do you get? You get 216.09, and you always round up. Always round up. When you're talking about a sample size, round it up. So since I get 216 plus a little bit, we're going to round that up to 217. Always round it up. That's because that's the safest thing to do, is to round it up. And that is a perfect place to stop. And we will watch this video because it's the Students' Tea Guinness Brewery thing. It's kind of interesting how the Students' Tea came about. Are there any questions? All right, we'll see you on Wednesday.